Let's say we're given a sample of particles with varying sizes and wanted to sort this sample such that we'd only be left with the largest ones. If we didn't have access to complex equipment like a centrifuge, what would be the best way to approach this problem? Or, for a more practical example, let's say that we have a sample of blood and we'd like to run a test where we first need to isolate some of the physically larger cells, like the white blood cells and presumptive circulating tumor cells. Well, how could we go about accomplishing this? One of the most clever ways to sort cells by size is through a process known as deterministic lateral displacement, or DLD for short, a phenomenon discovered by accident back in 2004. If we're looking for how we'd predict particles of different sizes to flow through a channel, it's important that we consider the distance between two individual micropillars denoted with a lambda. But since we're also looking to sort, we should also add a couple more rows where the distance between them can also be denoted with lambda. The issue is that this actually doesn't do anything to encourage larger particles to be sorted out. Flow will just push all particles downwards. So the creative step here is to add some slight phase shift to each consecutive row such that larger particles will be more likely to bump into the pillars and to continue travel in a diagonal direction. The ratio between the phase shift and the pillar gap is also known as the row shift fraction, and as it increases, the threshold size for particles to be bumped rightwards also increases. It's also important to notice that particles tend to follow the flow lane which they're a part of. To better visualize this, let's redraw a DLD and roughly trace two flow lanes where any fluid to the left of lane 1 will flow to the left-hand side of the second row pillar, while any fluid to the right will continue to flow to the right for the time being. And what this means if the particles are small enough is that they'll simply follow the path of the fluid and randomly zigzag back and forth such that the vast majority will, statistically speaking, fall pretty much straight down, similar to a game of Plinko. However, this isn't necessarily the case with the larger particle like this green one, which overlaps with both of the flow lanes. As a result, it becomes incredibly difficult for the larger particle to pass completely into lane 1, and so chances are the particle will constantly be pushed to the right as it passes through each consecutive row. Once we understand that the larger a particle is, the higher of a chance it has to keep being pushed to the right, the results of the Huang paper start to become a lot more clear. Because the yellow particles were the largest, they had the highest chance to overlap with flow lanes that pushed them to the right, whereas the smaller green particles were more likely to just follow the general fluid path without any significant lateral displacement. And if we go all the way back to the question of how we could separate a white blood cell from red blood cells and platelets, the answer to the question is now much more apparent if we were to implement DLD. To put it all together, the CFD model shows how white blood cells interact more with the pillar geometry, which constantly forces them to the right, while the smaller red blood cells exhibit a more randomized zigzag behavior. Problem solved.